Good afternoon, everyone, and thank you for coming to my Sure Research meeting. I will be discussing the biophysical molecular motor proteins in a crowded medium, and I was honored to have Dr. Savranda Tripathi as my mentor. So, uh, first thing I want to talk about is some background and goals that we have here. So, first of all, the cellular medium is it's very crowded. So these are all how a cellular medium looks, an image of it or a picture of it. Um, and you can see there are a lot of organelles, and so it's like just like you have a lot of traffic in the highway. Sometimes it makes it hard for you people to move around, and so it just like this in a cell, it's gonna make it difficult for proteins or beads or whatever to move around. And so we kind of wanted to replicate that in vitro. This is in vivo. We want to replicate that outside of a cell by changing the viscosity of the substances that the beads will be in. So a beads are like a little particle. So we changed the viscosities. And so we wanted to determine the viscosity of a glycerol solution. And so we can, see observe how the non-interacting proteins and how they function inside there, and how the interacting proteins do as well. And so, we have, we took a single molecule approach with the optical tweezer, but we had to set up a brand new lab in order to do so. So these are like the kinesin dyneins are moving. These are motor proteins. These are like the highways and microtubules. They're like highways the for the cell and for the proteins to go on. So what did we ultimately do? Well, we set up and calibrated an optical trap. It took quite some time, and I'll discuss it a little later. We prepared buffers for our solutions and for making the tubular microtubules, and we measured the viscosity of water using an optical trap. So this is an optical trap. We start with a laser. So see that thing all the way in the back? That's the laser. It's going to shoot out a laser. It's actually invisible to the human eye, so you have to use like a little cart in order to see it. Um, and we have some converging lenses. It's going to make it a little bigger for the beam. It makes the beam a little bigger for you to see it, to cover more surface area. We have mirrors that redirect the beam, so you can take it into the microscope. Eventually gets to the microscope. Some polarizer to filter certain wavelengths. A camera right here to record what's happening on the stage. As we have the stage, the microscope goes in. The laser goes in the microscope. It goes through the objective lens, and it hits on the cover slip, and where it'll be on the stage right here. And we have a position sensitive detector right here to record the coordinates of the movement. And we have a lot of software we have to use in order to record the data and control the stage and whatnot. So talking more about the trapping mechanism, so we have like I said, the laser beam goes to the cover slip, and because of the pressure that the laser beam has, it's going to trap the molecules and the particles. So you can see here, this is a laser beam. We put a filter on so we can see the beads and not just the laser, but the laser is still there. It traps it. And so these freely moving beads, they're no longer to move so freely, but they still oscillate inside that laser. So see, it's like a little spring oscillating back and forth within the laser, but it's now part of the laser. Now it can't really escape it, and so we can move this this bead wherever we'd like on the stage. And so what we found out was that one thing that we looked at, we wanted to see the correlation with the power of the laser. So how much milliamps we put into it, and the viscosity. So the solution. So as you can see, increased power, well, that results into increased temperature, and increased temperature, well, it really leads to the solution becoming less viscous, and so it's more fluid. And it's a pretty strong correlation, about 0.9 coefficient of correlation. So some future goals we had, we want to look at the biophysical characterization of motor proteins in a crowded medium with a BSA crowding agent, and we wanted to measure the effect of BSA on viscosity. So we have a lot of work to do. We're going to be we're working on this for many more months to come. It's really just the beginning. And so some personal impacts and exposure I've had so far in these 3 months, I've learned a lot of very important lab techniques. I learned something about making a flow chamber, which is basically a slide and then a cover slip and some tape on the side. It's very simple, but something I didn't know. You put the solution in there. Some programming with the LabVIEW is a very important program we use. Allows us. It's a program that you can use to make something like to track objects. So this LV core is something that tracks the objects inside the cell, important for coordinates. And we also do a lot of data analysis and overall operating microscope, cleaning it and all that stuff. So thank you.